We're on with Introduction to Computer Graphics, Shadings, and Material. Again, the sources, the classical book is here, and the real-time rendering book is the classics for the raster approach, and the ray tracing approach is based on the book from 2014, Computer Graphics Principles of Practice. If you want to go in deep, especially with the shaders, then please take a look at the respective books or visit some online resources, especially for shaders. There are really a lot of them. So what did we do until now? We looked into transformations from model space to projection. We looked into meshes. Now we know that there are models with points, polygons. We looked into the lighting of scene with the emission of light rays and the irradiance of pixels. But what we are missing is what actually happens on the models with the light that should meet the pixels. So that's actually what we're going for with shading. And there's one single slide on materials. I'll walk you through a little bit of Blender to give you just the complexity of the whole thing. And yeah, we can actually take a look at that. Okay, so what is missing? What colors do pixels have? Each pixel on the screen gets assigned a point in a 3D world, and this material or this stuff that is lit up by the artificial light then should reflect or absorb light and has a material assigned that defines how it does that. So what we actually need is some method to reflect the properties of a material that is assigned to a specific object that fills the pixel on screen, more or less. So the duck, again, the duck with lots of polygons. Every single point of this duck is yellow, but it's shaded differently. That's the whole thing, that's the idea. And with the shading, we actually get more ideas on what it actually does. Okay, so for instance, what do we see? There are lights. So depending on the angle of the pixel to the light, it gets darker. So the more it looks towards the light, the more colorful it is, the less gray it is. But also there is a shadow cast from up here down there and and down to the ground. And yeah, as you know, this is not part of shading. This is extra. And in here, there's a little bit of ambient shadow, stuff like that. So that's kind of even more extended. There are problems around the eyes. I don't know if you see them here. There are block artifacts that can have several reasons, but most likely something is wrong with the model. So either there are points wrong, there are faces facing in the wrong direction, or the normals are not correctly set. Because if you recall rightly from last time, the light or the direction towards the light is based on the normal of a plane, a normal of a triangle, a normal of a polygon. And if this normal is not set correctly, for instance, in the wrong direction, or if it's explicitly set to look at in another direction than the actual normal, then something like that happens. I'm trying to click yes. Awesome. So what would be those lighting models? There is the Phong Reflection Model, and that's a model for local lighting. And actually, local lighting is the thing that we always meant from the last time. It's the one that has no secondary reflections. So we consider only the light, and we do not consider shadow, because we think that every object is lit as if it was the only one in the screen, and that things that obstruct the path towards the light do not exist. It's a very nice model because we can explain it very easily. For instance, with the three components that we have, it would be the ambient component, the diffuse component, and the specular component. So we can also visualize it. So the ambient component is light from all directions, so it's just blue. Then the diffuse component is the component that has a very rough surface, an even but rough surface, so very small notches and crevices that basically do not reflect the light towards the camera. So you would have diffuse lighting, so maximum diffuse lighting, and then we would have specular lighting, which gives us the specks that are the mirroring basically the light. And if we just add them all together, we got the Phong shading or the Phong reflection model. Actually, the Phong reflection model, because Phong shading is then based on the Phong reflection model. The ambient light is tied to the scene, so it's there. If you looked into the exercise from last time and fooled around with it, the ambient light gives you just these color blotches. It doesn't give you any 3D impression, but it lights up the dark sides of, for instance, your torus or a box or a sphere, whatever you put in there. It's independent from the location of the light source and the camera, which the others are, of course, not, because the diffuse component is very much reliant on the angle towards the light. So depending on the position of the light, the color of the pixel is shaded differently. So, of course, perpendicular light rays, irradiation is at max. We have this angle in here, and the smaller this angle, the higher the light. It's not affected by the camera position because the light is emitted in a diffuse way, and that means in all directions at once. So it doesn't matter where the camera actually is. But it matters where the light is. Yeah, and the specular component, this is kind of the weirdest stuff, but it makes it look nice. In a way, it's shiny highlights on a surface that could be, for instance, polished metal or plastic, smooth plastic surfaces, something like that. It depends on the normal of the point plus the vector from the point to the light source and the position of the camera. So if you move the camera, the specular highlights move with the camera, even if the light is not moving. Here. And that's what I hope you to see in this small video. So maybe you see that the shade is moving because the camera is moving around the sphere, but it's moving at a different pace than the specular highlight, because the specular highlight is depending not only on the light source but also on the camera, so they move differently. That's the idea. Okay, so that would be the model, how you create a lighting or shading program that does the trick for you. However, we need to talk about two more things before we actually go into how to compute that. We have to talk about flat shading versus Gouraud shading or smooth shading. So there are different types of shading because we have these small polygons, and of course for a polygon, each pixel or each fragment on the polygon looks in the same direction. And if you do that, only the light source is moving, or the ball is also moving. No, the ball is definitely not moving because you wouldn't see that. But you asked me too fast if the light is moving or the camera or both. I think not both. I have to dig up the original Blender file to see that. But what actually is the point is that the difference in movement of the spec versus the shading depends on the position or the relative position of the camera and the light. So if you move the light or the camera, it's the same thing, basically. Or the effect would be very similar. Yeah, so simple approach is flat shading. Every fragment of a polygon looks in the same direction, and therefore it gets shaded the same way. So one color is applied to polygon, and as you can see here, the specular highlight would be on a quad here, and there are two more quads that have same color, two more that have darker but the same color, and then those four around it. This is typically based on the center of a quad, like here, where I put the red dot, and then the normal is computed, and then the color is applied to all the fragments or pixels of the polygon. So you can actually see that in Blender, and from year to year, I totally forget how to turn on the normals, but you can turn on the normals and then take a look at it. So, but let's take the screenshot here. You see a sphere based on triangles, and you would see the turquoise lines here sticking out at the center of the polygons. Yeah, looks a little bit like a hedgehog with a baldness problem. But that makes the whole color for the polygon. So this one is lighter and this one is darker, depending on the normal, which is the small turquoise line in the center of the polygons. In contrast to that, of course, we do not always want this low poly style or have so many polygons that you don't see the polygons. We often want to fake the shading a little bit based on less polygons than we actually want to convey to the viewers. And for that, we use Gouraud Shading, which is computed once per vertex and not once per normal of a plane. And there we have potentially different color per vertex. So if we have a triangle, we have 3 vertices, and each of the vertices has a different color in Gouraud shading cases, or in most Gouraud shading cases. And the rest of the polygon is filled in by blending between those vertices. So we determine how far is a point on the triangle away from vertex 1, vertex 2, vertex 3, and based on that, we linearly interpolate the color. So let's take a look at that. So this is the same model, but the normals are now indicated differently with the blue lines. And as you can see, there is a blue line on each of the vertices. So how do you compute that? Of course, you have input here from 1, 2, 3, 4, 5, 6 different triangles, and each of them has a normal. And for instance, you can average them. There are multiple ways to do that, but you can average them, for instance, and then you have normal sticking out there. And then you have a color here, and then you have a color here, and it's mostly the same color, so there will not be much change. But here on this point, there is a very different color, and so this part, linear interpolation, has a darker shade. So that's the whole idea. And although the phases are still the same, you see that the sphere looks much smoother than the other one. So you have both to compare, left and right, and flat shading is, of course, on the left, and Gouraud shading on the right. And Gouraud shading looks much nicer, more appealing, and a little bit like a PlayStation 1 game, of course. But the more polygons you have, the nicer it looks. So what is actually the problem with Gouraud shading when it looks so nice? The problem is that the quality still relates to the number of polygons. Less polygons, less quality in shading. While you might not notice, it's still the case. And what actually gives it away is the silhouette. So silhouette is here and here and here, and I just put it here. You see the outlines of the polygons, so it's not round. While I can apply a material that looks interesting, like here polished wood with 2 different ways of roughness and spec characteristics, we still have this rough silhouette of that. There is actually, I don't go into all the details of rastering and real-time rendering. It's far too much, but If you are wondering if we can do something about that, yeah, the process for that is called tessellation. We can invent new polygons and then make the silhouette also smoother. If you want to, if you go close to an object, then you can tessellate it. Specular highlights turn out to be very small for Gouraud shading, while they are big, at least one polygon big for flat shading. And if they're completely inside a polygon, they might even be missed. So you don't even see that. And if something is moving and then the specular highlights turns on and off again, depending on the distance to the vertex, then this gives a flickering impression and looks bad. Okay, so how is this actually implemented? Nowadays, and I'm just talking about nowadays. Nowadays we have shaders. By the way, I don't. On my computer, shaders do not work in Chrome, so I have to use another browser, Brave, to actually get everything running. But what can I do? I got it running, but yeah. Nowadays, computers should have shaders. What are shaders? Shaders are small programs that run on the GPU, on the general purpose processing unit nowadays, but it's actually the graphics processing unit that controls the rendering of graphics. And a shader can not only give a color to some pixel, but it can also manipulate vertices and pixels. So that's the cool part. So consider you have this sphere and you want to have the sphere tessellated so that it looks rounder in the silhouette. There's more polygons, then you can do still that with a shader. That's the idea of it. Why would you use shaders? On a GeForce 3060, 3584 shaders can run in parallel. So that's quite a lot, actually. Much more than we actually have on a common computer. And on a Radeon 7600, 2048 shaders can run in parallel. So even the cheaper graphics hardware is very, very much capable of running shaders massively parallel. And the cool part actually is that these shaders, I mean, it's on the one hand, it's cool because you can do more stuff. On the other hand, it's of course complicated because you can do more stuff, then things get more complicated while doing special stuff. It's like using a game framework compared to using a game engine. In a game framework, you can program your own graphical user interface, so it always looks like you want it. But on the other side, you have to program your graphical user interface because there is none included. And shaders are a multi-purpose tool, so they are really good at that, what they do, but they can do everything. And that turns out to be complicated if you want to do some special thing. Shaders advance the rendering capabilities and make the rendering pipeline programmable, and that's actually a fun historical fact. Nowadays, we all have rendering pipelines that are programmable, but before that, we had fixed pipeline components, and these pipeline components could not be altered from the outside. So if you wrote a game, then you created the 3D world and put it into the rendering pipeline, then yeah, you became an outcome at the other end, but you couldn't interfere with the outcome in between the input and the output. And nowadays you can change components in the rendering pipeline by writing shaders, for instance. So that's quite cool. Again, makes programming more complex, but of course you can then use pre-generated shaders, or there are, for instance, in Unity, you have a library for that. You can download shaders of other people, and you have a great shader editor and whatever. Okay, shaders, those little programs, there are generally two types of shaders, the vertex shaders and the fragment shaders. The vertex shaders process vertex data, which includes position, normals, color, and so on. It should primarily compute the final position of the vertices. For instance, apply a rotation matrix for animation. So if you have vertices, for instance, that move around because of a visual effect, particle system, you can do that with the vertex shader. And the fragment shader, or pixel shader, runs for each pixel potentially shown on the screen. So it can still be dropped, the pixel, but potentially those that are on the screen, computing the light interaction for a texture pixel. So that's the basic idea, but of course you can do more. Then you have geometry shaders, which invent new geometry, like creating additional vertices and primitives from existing ones, like creating grass or fur or hair or something like that. And compute shaders, which are used for general purpose computational tasks, for instance, particle movement. So I have these nice 500,000 particles that make up my smoke of the bonfire. Where do they go? You can compute that with a compute shader, and then let the geometry shader add additional ones on the bottom or near the fire pit, and remove those that are outside of range or experience the end of their lifetime in the particle system. Okay, so I talked a lot about shaders. A lot of top-down information. How do we actually program this stuff? So the language depends on the framework. First, good information. There is no unified shader language. Everybody has their own. I mean, nowadays everything converged kind of towards GLSL, OpenGL shading language. But there's of course still DirectX around, or still, I mean, has a large market share. It uses high-level shading language, GLSL, and we have Metal. Metal, which is the Apple thingy, has another shading language. So everybody has their own. Typically, you use something like Unity, Unreal, Godot, or something like that, and they support one shading language, and then transpile it to all the others, hopefully, hopefully correctly. So that would be taken away if you want to render your game on DirectX and then on Vulkan, then definitely you should not be the one to reprogram all the shaders, because as they're doing the same thing, most of it should be done by a transpiler nowadays. A basic shader structure is, of course, you declare a version of a shader, just very much like an HTML file. Then you declare the variables, and then you have the main function, so the programming code. And those are part of a pipeline. They are connected to each other, as we said, with the rendering pipeline. And what you need for a pipeline is an in and an out. Yeah, pipeline would be, for instance, a skiing lift. And the in for the skiing lift is the station in the valley. And the out is the station on the top. And if you have another station that goes up, whatever, even higher, then you would enter the in of the next pipeline component to go up to the next out. So we have in and out variables, and they actually have to match the input of the next shader, or the input of my shader has to match the output of the previous shader. And the uniforms are global variables, so everybody can access them. So do shaders have a shared memory? No, they don't. That's actually not a good idea, because you can never know when what shader does what. So they are massively parallel, and then having something like a dining philosopher's problem by having a uniform that only one shader can write, but a lot of them can read, but not while writing, then you would block out most of the other shaders, and that would defeat the purpose. That's the whole idea. So the output goes on the screen. It doesn't go back to the system RAM or something like that. They exchange information in the pipeline, but they have no shared memory per se. That's the whole idea of the shader. It's also rather costly to access the memory. So yeah, you can see it in those machine learning tasks. As soon as your data exceeds the RAM of your graphics card or your computational card, then everything gets slow, because you have to move back and forth between system RAM and video RAM, and that takes time. So what are the data types of GLSL? So we're looking into the OpenGL variant. The data types classically would be int for an integer, float for floating point, double for double precision floating point, then the unsigned int and the bool. I think there are more really, but I'm not very much into shaders. Especially for shaders, if you have something you want to share with your colleagues, which I do not say, maybe because I do not know it, but I'm not very well versed, as I said, with shaders. I only know the basics. Then just tell me in the chat. Or if I'm missing out something that I have to include next year, please also tell me. Yeah, what else do we have with vectors and matrices? Vec n would be a default vector of n floats, so vec3, vec4, and matrix of n by n floats would be met n, like met3 or met4. And that's what it looks like. So that would be now long talk short. This is a shader, and what does it do? It's a tricky question. Anybody from the chat knows what this thingy actually does? It's also my way of determining the lag, which might be really long now. Or you're frantically typing it into Shader and see what it does. That might also be the case. Yeah, so what it actually does, let's take a look at it. We have a fragment color, which is an out. So we create a fragment color, and we have an in of a fragment coordinate. A fragment is basically a pixel on a polygon. Something related to mouse movement, changing the pixel color. Yes, basically that's it. Thank you very much. The Ender Noodle gave us the real answer to that. It's changing the color of a pixel. So what we have is frag color. And we change it based on the absolute value of the coordinate minus the mouse coordinate divided by the resolution. Because of course the resolution would be whatever, 1280 by 720, and we need the color in between 0 and 1. So we divide it by the resolution, and then we get some fun example here. Let's see if we can show you the fun example. Yes, and of course we need to output it to the screen, otherwise we will not see it. So shader toy is still running. Shader toy. Okay, here it is. Hello. No, I wanted you to look like that. So wait. No. Why doesn't it? No, it doesn't like me. I wanted to go into full screen. Here we are. So that's what we have here in Shader Toy, and we can basically click somewhere, and then depending on the mouse, it computes the new coordinates, and it does that in full screen or in not full screen. That's the magic of iResolution .x and y. With Shader Toy, you don't have to think a lot about all the inputs because they have a lot of them. So there is uniforms, as I said, actual variables you can access. Can I? Here, no. It doesn't work. So we have the mouse, which we also use here, iMouse, and we have other stuff like iTime delta and iTime, and we can actually drive that does something. Oh yes, a redefinition. That is always very nice if you create the definition of a variable twice. We definitely have to also leave it alone. And yeah, that's now based on the time. So now it changes over time. Yeah, it doesn't look like it makes a lot of sense, but no, I don't want to. But now let's take a look at the crazy stuff that other people are doing. And I really like to show you these things because this is the same approach. It's using shaders, and you can do something like that here too. I mean, this is very nice. There are even more complicated things that you can create. And it runs with 60 frames. It's capped by 60 frames, and it's a little bit longer here. But there are many, many different very nice shaders. Butterfly flag. Oh, that one looks cool. Alien core. Let's look at that one. Yeah, and it even runs on my computer with a 10 frame per second webcam. Okay, anyway, let's stop this one and go back to the slides. That's the way it works. Oh, now it works. Okay, great. So there is this video, what are shaders? And I just put it in there. I won't play it because then most likely I'll get a strike on YouTube. So if I upload the recording from the lecture. So please, if you have time, take a look at that. There are actually really cool videos on YouTube and other places about shaders. There's a lot to learn about shaders. Just take care. There are a lot of people who have no idea about shaders and then make videos to grab the views. So the best approach you can actually do is trying it out, and there is official documentation also on shaders. So yeah, it's hands-on is your friend basically. So how does shading and processing actually works? Processing comes, or P5JS comes with the default pixel shader, and we can use WebGL shaders with a vertex shader and a fragment shader, and it follows the WebGL definition. So if we want to create something, I totally forgot again to open up the editor. Let's see if I can fix it real fast. I'm not logged in, so I will switch to the webcam that I don't record my own login screen again. Oh, I mean, let's see if I get my catches right. Put this one back on. And then it should be something like 05. Yes, this one it is. Is it this one? Or is it? Oh, yes. That's the one. I was just really at the wrong file. Okay, let's take a look here. Easier to see. What we actually need, we have to load those shaders. That's here. Loading the shaders from files. And then we can enable the shaders and do something with it. Yeah, so for instance, here we create a sphere, and the shaders are the ones that we are using. So it's not much of a fun experience. So the fragment shader is just giving us a fragment color based on the vertex color. And the F is the Gouraud factor, which we create here as, where is it? Where is it? Where is it? Varying float Gouraud factor, and that's the in here, and the fragment color is the out here. Okay, running it doesn't run. why it does not run. There might be an issue with the argument pass. Yay. Did I tell you that shaders do not run on my on my Chrome thingy? Maybe I did. Let's embed this one here, which was anyway the right one, and then open it here and run it here, and yes. And here we just have a Gouraud shader. Sketch.js. We have a torus and a donut, a sphere and a donut flying around it. Okay. Let's take a look at the shaders. As I said, the whole idea is to create a color per pixel, which is this one here, the fragment color, and it's based on something that is determined by this vertex shader, which is basically a normal, which is the dot product of the normal of the vertex and the normal of the light. With that, we basically have our Gouraud factor and then can determine the color. So it's interconnected and a pipeline. So yeah, it's very little code for lighting up the whole scene. So let's take a look at the Phong shader, which follows the idea of the Phong Reflection Model. Ambient plus diffuse plus specular is Phong, very easy equation here. And it would look like that. So we have the, again, the vertex shader, which is on the left side here. And again, the normal is based on the light and the actual normal of the pixel. And then we use this information to create the specular highlight. We create the diffuse shading, and we add the ambient color here. So these are the three components. Yeah, and just to remind you, we are in an interdisciplinary lecture, so especially for those with a non-computer science background, you might not go into shaders knee deep. So this is just for your information and will not be part of any exam or something like that. I just felt weird not talking about shaders in a computer graphics lecture. So also that you understand the basic idea of shaders and see a little bit of the complexity. And there are people who like to program this stuff, and there are programmers who don't like to program that stuff, and that's also totally okay. So if you're a game engineer, then look into shaders. If you're more leaning towards the game studies side, then understand that there are shaders and have a rough idea on what they do, and that should be enough for the interdisciplinary part here. What else is out there? We have, of course, a lot more shading models. For instance, Lambert, which gives a perfect diffuse reflection. For instance, coal or snow, they typically do not have highlights. And another thing would be Oren-Nayar shading for rough surfaces. It models the small notches that are not inside the 3D model and reflected light from other notches, like you can see here in this picture. So there are many more. I don't want to go into detail, but Phong Blin, which is the default on OpenGL, and Cook-Torrance, which also has specular highlights, but takes microfacets into account. Okay, so many ideas what you can do. What they all come together is that depending on the model and the material used shading, And material actually defines what happens with the light on a surface through scattering and absorption. We can have diffuse and specular reflection, subsurface scattering, glossiness, colored specular highlights, emission, and so on and so on. This is currently a combination of color, shading, and texturing. So textures are, you have image textures are limited to what you put in. And at some point, the image is not enough anymore if you go into deep. Shading color can do more, and of course, procedural textures can do more. But making these materials is an art on its own. And what I wanted to do for, say, 10 more minutes or something like that, and then you're off the hook and can go for coffee. Other than your own home coffee machine. I wanted to look into Blender to give you just an idea on what can be a material, and I also don't want to go into this is now the what we all do, but just to give you an idea on the possible complexity. Okay, my computer beeped. That's okay, beeped because of something else. Okay, we had that. That is Blender. No, doesn't like me. Can't I just make it full screen? Oh yes, that's what I want. Yeah, and I just noticed that I didn't install the key mapping. I'll just tell you what I do, so you don't see it, but can remake it. Okay, so now I actually have my mouse and I can look through the camera with a screenshot, with a keyboard shortcut, and there is my light, which I can move up and down, and I can turn on, of course, shading so that we can see the influence of the light here. Okay, but what I actually wanted is I wanted to show you about the materials, and for that I'll just put on here a plane and add some more stuff, like for instance an icosphere. Here, here, a little bit back here. Okay, and move this one away. Here. Yeah, something like that. Good. And we can see a little bit about shading. And now we go into this shading stuff here. And yeah, we're back. And we can change what it looks. Okay, so one thing would be we can actually say, I'll just remove the cube here and the plane. Cube, go away cube. So we can just see that one. So we can change to smooth shading. Then, as I said, it looks like a sphere, but you can see the silhouette. We can shade it flatly, and what we also can do, we can do it auto smooth. And auto smooth is out up to an angle, and then goes into flat shading, which totally makes sense if you have something sticking out of that. For instance, wait, I can make something stick out of that. I'm good at that. Not very good at modeling, but I can at least make something completely crazy out of it. Then go back to shading, and with the auto smooth thing, you can see that it doesn't smooth it out completely. If we make it like that, it kind of looks weird, which we don't want. And with auto smooth, it creates something like that. Okay. So what I actually wanted was shading back. What I actually wanted is to create a new material here. And with the material, we can actually change the color. Make it blue. blue is always a little bit better here. We can change the roughness. So if we have the roughness like that, it's very diffuse. If we make it very glossy, then we can see a reflection of the lighting here. So that's pretty cool. We can go in between like specular highlights and reflections. We can make it more or less metallic, like now it's very metallic. Now, yeah, and now we have something like a blue metal ball. And yeah, BSDF, I'm not really sure if I can change the shader here. No, I think I have to change it here. Yeah, as you can see, if I go over that, here you can use Lambertian Oren-Nayar diffuse reflection. Put it in here. If I use that one instead of blue, then it looks very different. Okay, so this one glossy and everything, and this one not good. Okay. Now for a material, I can actually Shift A add stuff. I can actually add an input color. Maybe I want that. I want to have my blue here, and want to have the base color the same so that I can switch between them. And for materials, you typically combine stuff like delete with X, of course. For that, you typically combine stuff, so you can use a glossy shader, for instance, or a metallic shader, and so on. So let's use a metallic one here. And we use the base color on both of them. Let's go here. And then we have this metallic shader, but we want to have a diffuse component too. Nice. Oh, no rotation. We want to have a diffuse component too. So what we can do is we can use an add shader. Why did it do that? Put it in between here, and this one too. So we have both shaders on it. Okay, so that's a cool idea. And then we already have a material that uses two shaders. And to make this one even more interesting, we can use a mix shader. Yes, and moved away. Don't move away from me. Mix in here, mix in here, go here. And then we can say we want to have it more metallic or more diffuse. So that's the cool idea about it. Okay, so that might be just a material combining two different shaders. As you can see, we can have the color here as an input, but what we can also do is we can define a dynamic color, which is also fun. We can have a texture, and for instance, we take wait, what do I want to have? Let's take a Voronoi texture. Voronoi is always cool. I want to have the color in here as the base color here too. And so you can see that we have a different color for each of those Voronoi thingies. And we can set up different stuff. But what I actually wanted to do is I wanted to have distance to edge. Wait. Where does it show? Distance to edge. And yeah, that's what I wanted to have. Then we have this crystalline structure here. And what we can, for instance, say is we can have it just in a diffuse component. And for the other one, we can actually use a color, whatever. What would be a good color? color, the one we want. And again, let's take blue. So we have a blue metallic thingy, and the diffuse color is then made of these scale things or crystalline structures. So that's pretty cool already, but it doesn't help us too much. So what I actually want is I want to have something that looks like it has this crystalline look, but has a material that shines through. So instead of having two materials lying above each other, I want to have one that gives you the color, a reflection, and diffuse lighting, and another one that changes how it interacts with the light based on, for instance, a crystalline structure. And for that, we do not change the color, but we can change the normal. And if you remember, if we change the normal, then we also change how the shader behaves. That's the cool part. So this doesn't do anything. Why it doesn't do anything? Because here we get the distance out. I'll just show you by connecting it here. This just gives us color, not a normal. That's the. So we actually want to have a normal and not one single color in 0 to 255 grayscale, but we have to convert that to a normal that gives us the distance based on the gray value, the distance of the point from the surface of the polygon. And that's what is called bump mapping. So let's see if we find displacement bump here. Yes. No, we put it in as height, we put out the normal, and then we hope that this kind of does something. Does not do anything. Let's put it in here too. And let's say invert, that's often a problem. Ah, here we are, the distance setting was it. So now we actually have a crystalline structure in a way. I'll invert it back again. And yeah, so it shades the metallic part with the normal that actually comes from the sphere. And it shades the diffuse part with the normal that actually comes from our bump map. If we do both, then you see it changes a little bit here. So that's the cool part. What you can also do is we can put it into displacement. Then it looks really crazy, because then it changes the geometry. Okay, so that's one idea that is totally strange in a way, but that's how you create stuff in here. And there are of course more ways to create stuff, and I'll look at it with you in the Blender workshop. But yeah, Material Designer or Unity or whatever, most of those work with these input-output graph systems, where you create an output from several inputs and combine them somehow. And yeah, there are cool tutorials on that for Blender. For writing your own shader programs, this is of course more complicated, but yeah, again, Unity has a visual shader editor that looks a little bit like that here. Okay, so that's all I wanted to talk about with shading and materials. Are there any immediate questions? If not, then say thank you and stop the recording right now. Goodbye.